access dashboard. First, let you know what is the AI/ML fabric deployment. Cisco Nexus dashboard here provides a comprehensive tool to manage the network fabrics of different types. When first going to the next dashboard, I'll create a fabric. Once in the select type page, we'll pick AI/ML. AI/ML. Then the user can choose between AI/ML routed and AI/ML VXLAN EVPN fabric. In this lab, the AI/ML VXLAN EVPN fabric is selected in here. On the setting page, the user could configure the fabric's main parameters, like the name, like the location, BGP, AS number. I'm going to select the AI/ML CoreOS queuing policy. From this drop-down menu, we're going to select like 400 or 100. The telemetry collections also can be enabled at this stage or later if needed. So on the next page, the user could view and edit the advanced setting. The default settings are suitable for most of the use case, but they can be changed. On the fabric summary page, a user can just review and all the previous configure selected parameters, and we're going to click this submit. After the fabric is created and switch is onboarded, the QoS policy will be applied automatically on the switch level and on the fabric link level for the access ports where the servers are connected. The respective policies will be activated during the interface configuration. So by setting checkbox in here, enable PFC and enable the QoS configuration. We're going to talk about the PFC, ECN in later topics. Okay, now let's talk about the how to optimize the AI ML network traffic. Optimizing the network traffic for AI and machine learning AI ML network. These workloads is critical because these tasks involve a large-scale network transfer between, the GPUs. So these transfer uses ROCE v2. It stands for RDMA over Converged Ethernet version 2, which relies on the UDP rather than the TCP. Unlike TCP, the UDP does not automatically transmit lost packets. So even a single packet loss can cause this GPU to wait for a timeout and resend a large amount of data, right? So this not only slows down a distributed training, but also it adds unnecessary loads to the network. In a worst case, if the GPU disconnect or degraded, the entire training job can halt. It increases the training time and the money. Okay. So the backend network must deliver a high throughput and low latency, and is a robust congestion management where easy to configure and capable of detecting the anomalies proactively. So now how to prevent the packet loss and maintain the performance. The Cisco solutions use this Nexus 9000 switch and the Nexus dashboard platform. The most effective way to manage the congestion and build a lossless Ethernet is by combining ECN. What's ECN? ECN stands for explicit congestion notification. Is a notification and the priority flow control PFC. PFC stands for priority flow control. So it's a flag for controlling. The ECN reacts first by signaling the congestion before before the packet the packet the packet lost or the packet drop happens. Where the PFC here acts as a fail-safe to pause. It pauses traffic if a congestion happens. So these two together, they form a data center quantized congestion notification, DCQCN. Data center quantized congestion notification. This is a mechanism designed for the RCE network. Both network device, like the NIK and your server, or the end host, must support ECN and PFC for this system to work effectively. Now let's talk about specific about detail in ECN. ECN I talk about is explicit congestion notification. The ECN helps manage the congestion by marking marking the packets when congestion detected. So it marks the marking in the packet IP packets TOS is a TOS field in the IP packet. When a receiver detects the ECN bit set to say OX11 and it will send a congestion notification packet CNP. This is the packet IP packet with ECN marked to the sender. It promising it to slow down the affected flow. So this flow will have to slow it down. The Nexus 9K 9000 switches will use WRED. It's a weighted random earlier detection to apply this ECN marking. The WRED sets two thresholds. One threshold is the minimum threshold for the minor congestion, and we have the maximum threshold. It's for the severe congestion. In the first place, only a percentage of packets are marked, will be marked. But if the congestion worsen, all packets in the queue are marked. So to proactive approach, this is a proactive approach, allows the endpoint to adjust their transmission rate before before the pack before the congestion or we have all the packet loss happens. Then next we talk about PFC. PFC. It stands for Priority Flow Control. The PFC was introduced to enable a lossless lossless Ethernet just by pausing the traffic to a specific priority level. So originally it's designed for L2 network, is it Ethernet. The PFC now works with the L3 by using the DSCP, this DSCP marking to maintain the traffic classification across routed hops. The PFC sends pause frame, say a hop by hop from the points of a conjunction back to the source, which can take time but effectively prevent packet drop. In this ROCEV2 environment, the PFC complements the ECN just by providing an additional layer of congestion control. It making sure that the critical traffic flows remain uninterrupted. Now, let me describe a scenario. Layer 3 server are connected through a backend network, all right? And ROCE v2 traffic is generated using the NVIDIA CCL test. Before the traffic starts, the ECN and PFC are disabled on the switch for queue handling, the ROCEV2 traffic, where this switch will have a WRED. These are remain enabled, all right? Just let you know, here is my backend. These WRED will be enabled for a small buffer to stimulate the congestion. At the start, say 0 minute, the traffic flow at the near interface bandwidth. So it's a lot, causing a buffer to fill and packet drop to happen. At the other 10 minutes, the ECN PFC will be enabled. So this switch start marking packets with ECN, and this is ECN bit, and send the PFC pause frame as needed. Then say this is destination, this is source server. Okay. When ECN PFC frame, they will be sent to the destination. Then destination server detects, okay, this is a conjunction, and signals the source server to reduce their transmitted rate. So as a result, the packet loss will stop and the network stabilize. So these shows how enabling the ECN PFC effectively to prevent the congestion and maintains the performance in the AI ML workloads. So now let's review the AI ML QoS configuration. I will review the actual CLI QoS configuration, which was applied to the switches by the Cisco Nexus dashboard. So this is a targeted configuration with PFC and ECN enabled. Let's open a fabric, go to the inventory. For example, we're going to pick the RTP AI1 leaf 1 switch, and we'll take action, maintenance, and we're going to show command. In the command fields, we're going to select the show and start the IPQoS, and we're going to click execute. Show IPQoS. The startup config is shown, and here and to the target QoS setting, start. Because running config here might be changed by automation for this lab, then let's take a look at QoS configuration. Let's remember this configuration was created automatically by Next Dashboard using the AI/ML Fabric template. We can notice that the CPM, the congestion notification packets, and ROCEv2 traffic is classified based on the DSCP value. If I highlight right here, the ROCEv2 traffic is mapped to the Q3, and the CMP traffic is mapped to the Q7. For Q7 CMP, the priority queuing is enabled to make sure that these packets are forwarded with the highest priority. For Q3, RCV2, the WRED with ECN is enabled. The buffer thresholds are defined automatically and depend on the selected QoS policy. Let's see this part. And this part. And we'll notice this part. The network QoS policy with PFN, with PFS is enabled. Let's scroll down to review the remaining parts of the QoS configuration. We'll notice that egress queuing and network QoS policy here are applied on the system level, and the classification policy is mapped to the interface. You can see what I just highlighted. So this includes fabric and access interface, as well as the NVE interface. Also, we'll notice the PFC is enabled on the interface level. Next, we're going to review some types of anomalies detected and raised by the Nexus dashboards, which are related to network congestion. Let's close this. On the Fabric overview page, we're going to click anomalies, and we're going to set the time range to last 2 hours. Here, we'll make sure all anomaly groups for easier navigation. In the list of the anomalies that we're going to find the throw events like a buffer job anomaly type, we're going to click it to see more details. I can see the list of anomalies that were triggered during the last for 2 hours. We're going to notice the detection time anomaly should be triggered with approximately 1 hour interval and at the beginning of every hour. Let's click one of the anomalies from the list. So here shows detail about the anomaly. We'll see it was triggered by packet drop on leaf switch, and we'll take a note of the leaf switch here is leaf 1. Here it reports the anomaly. If you happen to see the anomaly when it's active, you will see recommendations on how to fix it. Let's close this. Here we find interface egress high threshold anomaly type. We're going to notice like detection time here is also beginning of the hour and several minutes like 15 minutes, 4 minutes after buffer drop anomaly. I can click one of them to see the detail about the anomaly. Here I can find it was triggered by high egress utilization of one of the interfaces of the leaf switch. Here we can take note of the leaf switch interface and reported in the anomaly is Ethernet 1/1 on the RTP AI 1 leaf 1 in this example. So I can review the detail, the statics of the switch interface reported in this anomaly and to troubleshoot and investigate the issue further. So how do I do it? We're gonna click the inventory and I know it's leaf 1. So I will click on the leaf 1. Here you can see the switch view. The interface that was reported in the network congestion indication anomaly Ethernet 1/1. I find the interface operational speeds is to 100 GB. I can go to train and statics. I only it happened in the last 2 hours. I can click last 2 hours. Scroll down to the errors traffic. We can see the bandwidth graphs. So this is executed every 1 hour. So we can see several occurrences it represents in this graph. So we're gonna pick one of the occurrence for investigation. I can take the one generated at the same time as the anomaly that were reviewed in previously. But all of them are similar. We're gonna remember that traffic is generated started like 0 minutes every hour. The bandwidth utilization and the rates in transmission direction increased to level like right here to 90 or 95% is about 90 to 95 gigabit per second. At the same time, the error counter started to grow as well. Here you can see, you can hover your mouse and over the graph, you can see the exact value and the timestamp. All right, let's scroll down to what we just talked about, the WLED, PFC, and ECM. Here we see the congestion score, congestion detail in graphs. The congestion detail in here, congestion detail, contains statics about the WLED, AFD drops, PFN, ECN. We're going to notice in the view queue links for each of these counters, which allows to troubleshoot a potential issue at an interface queue level. So on this page, you could check the match events that happen during the congestion is all over. Here, job starts to grow, the congestion level increases, and where the PFC, ECN were disabled here, here they disable at the beginning. And later, the PFC and ECN were enabled, and job stopped it to grow. You see this flat. Congestion level then decreases, and the score over time decreased. I can see the queue. Remember, the ROC v2 traffic is the map to the Q3. If you remember the previous slide, I showed you the QS classification class map. You can see the time from 0 to 10 minutes. Also in Q3, at this time, the switches started to mark excessive packets with ECN bit. So we're done this, and we can notice like the Q3 increased to critical level. And immediately after job started to happen at like 0 minutes, which here indicates the heavy congestion already. After about 10 to 11 minutes, when job stopped it, the congestion decreased to the minor level, and it's still at a 0 level because the PFC, ECN were involved. So at a 20 minutes, when the traffic generation stopped it, the congestion score then would drop to 0, and the marking also stopped. Here, by checking the bandwidth graph, is not very obvious that on the 2-hour view, because of static collection and aggregation intervals, a real-time graphic can provide a better visibility. But when PFC and ECN are getting involved, the network congestion is signaled to the source server, and the traffic rate is decreasing to prevent further drops. When the situation stabilizes, the traffic rate increased again, depending on the algorithm on the end host. Here at 5 minutes, the transmit rate is reaching about 92 gigabit per second. Then at 10 minutes further, we could see the transmit rate decrease to 72, 71 gigabit per second. So as I talk about it, the PFC is a mechanism to signal the congestion and pause the traffic if ECN does not react fast enough. The buffer utilization continues to build up. So we currently just seeing the interface connected to the destination server. So this interface, we're not generating the PFC frames on demand in predictable manners, but it's still some PFC packets that might be visible to and from the destination server. We're going to check that the PFC was involved. We need to check the interface towards the source of the traffic. We have two sources of traffic in the scenario. So one is connected to the sense switch using the 1/2, and one is connected to different leaf switch. So it is reachable via the fabric interface. Ethernet 131 or 32. Let's go back to switch overview. Here we take a look at the port 1/2. It's the source traffic. Click train statics. Keep scrolling down. We're going to view detail PFC. We can see PFC transmission counter for Q3 increased at a 10 minutes mark. The PFC activation and pause frame counter depend on the traffic pattern and the congestion severity. When ECN is enabled, the PFC is triggered only if the ECN does not react quickly enough. If ECN is unable to handle the congestion on its own, the PFC may not be involved. The counters may just remain stable. The next topic we'll talk about is the dynamic load balancing DLB. Dynamic load balancing DLB is an advanced intelligent hashing mechanism that improves the traditional equal cost multipath ECMP forwarding. Unlike the static ECMP, which just distribute the traffic based on the fixed hash value, DLB continuously monitors real-time link utilization, and it dynamically redirects traffic to underutilized path. So this approach ensures the better bandwidth usage and it prevents congestion. It makes it particularly valuable in this modern networking environments such as AI, ML training networks, where the traffic patterns are just highly demanding and less predictable. Then what is this traditional ECMP? The ECMP is a common technique used to increase network bandwidth with enabling multiple equal cost paths between 2 points. So when forwarding packets, ECMP will use a hashing. Also, there's a hashing algorithm that's based on the 5 tuple TULPE, which is the source and the destination, and protocol is an IP, a UDP. It could be source ports and the destination port. So these 5 tuples to select their path. So all packets in a flow follow the same path. See, this is same flow, follow the same path back and forth to avoid out of order delivery. So, however, the ECMP has limitations. So, one, it uses the static path. So it does not adapt to the real-time conditions, right? And this will cause uneven distributed packet flows and causing some of the link to be like this one is overused, this link, and overload where this link remains idle. So even flows are evenly distributed, varying throughput among the flows can lead to this imbalance. So these issues are manageable in a typical data center with many small flows. We have many small these kind of flows. because it just was in the traditional data center, but it becomes critical in the AI ML flows network. So what is challenging in AI ML network? The AI ML training network often use we call it, they have a spine, we have leaf, this architecture, and exhibit traffic patterns that amplify the ECMP's weakness. So we have a few unique flows because protocol like ROCE v2 it uses UDP with fixed ports, reducing the hash diversity. So most traffic consists of the high throughput is an elephant flow between the GPUs, which can saturate your link. The GPU NIC cards operate full capacity will lead to sustained high utilization. So these factors can be polarizing, where few large flow congest the specific link, where the other, like this, remain underused. It reduces the overall throughput and spreading the congestion in lossless fabric. And here comes how the DLB solves these challenges. The DLB overcomes this ECMP limitations just by introducing a dynamic, adaptive load balancing. It monitors the real-time links utilization, like this link and this link. It monitors. And it will select the least loaded path for new flow. The Cisco Nexus switches implement a flowlet. This flowlet-based forwarding, where the packets burst within a flow are identified as this flowlet. Each flowlet can be sent over different paths. You can send here, you can send here, without causing an out of order delivery, which is critical this for RDMD traffic. The DLB also supports the per packet load balancing for the environment that allow package reordering, such as the small NIC cards. Just by distributing the traffic intelligently, the DLB ensures the uniform link utilization. It reduces congestion and improves performance. So combined with a feature like we first talk about is the PFC and ECN. PFC stands for Priority Flow Control, and ECN stands for Explicit Congestion Notification. So the DLB here helps to maintain a lossless, low latency network fabric. Also, the DLB will support the static pinging, will allow the administrators to fix the traffic from a specific source from some specific source to a destination when needed to use a specific link. So let us review actual dynamic load balance configure on one of the leaf switches. The DLB is enabled on my leaf 3 switch on uplink interface connected to spines. Let's go to my first fabric. Click inventory. You'll find leaf 3, action, maintenance, show command. In this command field, we'll make sure show and hardware profile DLB. Click execute. We can notice DLB is enabled, mode is full LED, and the full LED aging time is 5 seconds. The interface where DLB is enabled are Ethernet 1/31 and Ethernet 1/32. These are two interfaces connected to the spine switch. Okay. Then let's take a look at the interface statics confirming the even distributed traffic. So I will go to switch interface statics to confirm that the traffic is evenly distributed across the DLB enabled interface. The traffic for this lab is a single flow RCE v2 UDP traffic between two hosts connected to different leaves, which are also used in previous lab. Okay, look here, host have SAS31, SAS32. These two link goes to the spine switch. Let's close this. Find my leaf 3. Let's click the switch. And on the switch overview page, the interface selection, we're going to click the view interface statics. It's right here. Here it shows top 10 interfaces by drop-down menu. Here we're going to select is the transmit rate. And in the time frame, we select the last 2 hours, and it's real time. Let's expand the graphs for interface 31 and 32. So we can notice that transmit rate graph patterns and values for both interfaces are almost the same over time, and we could hover over the graph to see the values and the timestamp. Let's compare the transmit rate. This is 5.19, 5.18, 17. With the first interface at the same, like 31 and 32, same times. Remember that the traffic represented on the graph belongs to single UDP flow between the two hosts without DLB, using only the ECMP load balancing mechanism. All this traffic would be forwarded via the same physical interface. It can result in one link being overused where other is underused. So it creates the congestion over used link. Show you how a large language model, LLM, like the Llama 3.1-AB, is fine-tuned on an OpenShift cluster using the RDMA-enabled hardware. Unlike a previous congestion test, this is a real fine-tuning workload without any artificial issue. So why we use RDMA for LLM fine-tuning? The fine-tuning big models usually involves multiple GPUs crossing different like the servers. If you use normal TCP/IP networking, you can run into the problem like slow gradients sharing between these GPUs, and it have extra CPU work for the copying the data. The network also congestion that limits the scaling. So the RDMA here solves this problem just by letting the GPU access memory directly across the node. It's what RDMA does. So that means it gives a faster sync of the model updates, and it has lower communication overhead, and it gives the better scalability for large clusters. The RDMA also works well with machine learning frameworks like NCCL test. To fine-tune with RDMA, you will need the RDMA capable network cards like the Milan here Milan Milano Connect X NIC cards, and you will need a high speed links like you will need 100 Gbps links, or you will have more. And you have a powerful GPU, of course. It could be 800, or you could have H100 L40S. The machine learning framework will comply with the RDMA support. Now, let's talk about one thing. That is the LROA. It stands for low rank adaptation. It's a smart way to fine-tune the big models without using too much memory. Instead of changing all model weights, these LORA adds small metrics that adjust the model. Like it saves the GPU memory, it speeds up the training and keeps the model quality very high. Then next, what is the array? The array is open source tool for distributed computing. It makes it easy to run the training across many of this or GPU or servers. So Ray here automatically spreads work across multiple list nodes, and you can use these resources efficiently. It handles also these failures so the training doesn't stop. Fine tuning LLMs like this Llama 8B helps the business to create better AI solutions for the task like customer support. If you're in finance, it gives a finance analysis. Pre-trained models are general, but fine-tuning with your own data makes them more accurate for your needs. The traditional fine-tuning is slow and expensive. LORA fixes this just by updating, owning a small part of this model. So this is small parts of the model. It saves your memory, it saves the time. Here, instead, Ray helps scale this process across multiple GPUs servers easily. The RDMA makes the data transfer we say RDMA, makes this transfer smooth and the data transfer between the nodes faster. So together we have our LA and array and RDMA. They all create a powerful, efficient setup for fine-tuning large models. This lab will use a model called GSMAK from Hugging Face, created by OpenAI. It contains the grade school math, word problems to test the problem-solving skills in the AI models. Let's open Red Hat OpenShift. We'll take a look at the fine-tuning jobs. Click the networking and routes. We'll go to search the array. Let's find all projects. Under all projects, we'll search array. Let's click the array dashboard array. And right here, we'll click the location. On this cluster tab, it will include the status as well as insights into how resources are distributed across the cluster. Here I can see the jobs currently running and recently executed within my array cluster. The fine-tuning job is configured in a way to ensure there's traffic at the top of each hour. So each training epoch takes approximately 30 minutes on a 2-device setup. So back to the OpenShift, we're going to click workloads and pods. Make sure let's project all project. We're going to search a pod called array worker. It will have the names like array small group array worker. And we're going to open this and see the YAML tab to see its configuration. Let's scroll down a little bit. Here about the line 18, we'll see the attachment of the pod to the RDMA networks. Each network is connected to a separate pod on the ConnectX NIC cards. Let's take a look at how monitor traffic on an XS dashboard. The array head and the worker nodes performing the LLM fine-tuning are running on OpenShift worker. It's my server 1 and server 4. In here, the connect as port 1 and port 2 are connecting to my leaf 1 and port 2 is connected to leaf 2. Here, server 4, I have a port 1 and port 2. Port 1 is connected to leaf 3. Port 2 is connected to leaf 4, each on Ethernet 1. Let's click my leaf 3. From the interface section, I can see the interface statics. Here we use 2 hours. Or we could select the last 6 hours, click apply. So this will allow traffic from more than one training job cycle to be reviewed. Let's expand this Ethernet 1/1. I can see the top interface. The Ethernet 1/1 is targeted for our NCCL test. We can notice that the hourly spikes in the transmit rate. So all right, the lab will showcase you how efficient fine-tuning of Llama 3.1 AB instructed LLMs on this RDMA enabled nodes with a Cisco AI ready fabric network. Now it leverages OpenShift, LORA, and Array. Well, as so far we reviewed how you create the AI ML fabric in Nexus dashboard, and we talk about optimizing the traffic for AI ML traffic, ECN, explicit congestion notification, and priority flow control PFC, how they work to provide a lossless fabric network for our AI ML training. Later, we'll talk about the dynamic load balancing versus the traditional ECMP, equal cost multipath forwarding. And then lastly, we talk about what is the LORA, low rank adaptation, and what is array, and how they work together in IDMA fabric network to fine tuning the large language model Llama 3.1 on all these RDMA enabled nodes. Hope you enjoy. Thanks for watching.
Hey everyone, NetMaven here. Don't forget to hit that subscribe button to dive into the world of amazing network technologies with me, and please feel free to leave your comments below. Hey everyone, NetMaven here. Don't forget to hit that subscribe button to dive into the world of amazing network technologies with me, and please feel free to leave your comments below.